In this video, I'm going to help you understand the semi-permeable nature of the plasma membrane and how we move things from one side of the plasma membrane to the other. It all starts with this quirky phospholipid. Remember this? The most abundant component of the cell membrane or plasma membrane are these little blue molecules called phospholipids. And you can see that they go with their feet towards each other and their heads away from the center of the membrane. Why is that? Well, remember, some chemicals are polar. They have little regions of positivity and negativity which allow water to sort of squeeze right up next to it. So we say that it likes water. It's hydrophilic. This blue phosphate-containing head of the phospholipid is hydrophilic. The long fatty acid tails are nonpolar. That means there's no region of negativity or positivity. It's sort of all neutral. And so water doesn't like that. This is the reason why water and oil don't mix. And it's the reason that we say that the phospholipids' tails fear water. They are hydrophobic. So look at this. Is there water on the outside of the cell? Yeah, of course. Is there water on the inside of the cell? Yes. The ECF is on the outside, and the ICF, or cytosol, is on the inside. So these heads face the water on the inside. These heads face the water on the outside. You'll see in some of the videos you watch that they're sort of like balloons, like a level cloud of helium balloons. And they sort of stick together, but they can move up and down and sort of flow like a liquid. Which I just had to drink. Here we can see the short bullet point list of the things that can and cannot get through that phospholipid bilayer. Because the central core of the plasma membrane is fat, lipids, things that are nonpolar or hydrophobic can get through. Obviously, other fats can get through. Steroids, testosterone, estrogen, thyroid hormones, they can just melt right through the plasma membrane and affect enzymes in the nucleus. They don't need outside or integral peripheral proteins. Other things, and maybe a bit more troubling, but a lot of our heavy metals and nasty chemicals, pesticides, carcinogens, they're also lipids, and so there is some risk there too. Oxygen and carbon dioxide, obviously the most important gases that we talk about in human physiology, and the reason you have to breathe in and out. By their chemical nature, these are also nonpolar. There's no polar covalent bonds holding these together, and so these are also hydrophobic. Now here's the thing. It's very strange. Water is obviously hydrophilic. Fears fat, won't mix with it, but it's so tiny that even though it's hydrophilic and polar, it still can pass through the plasma membrane through a process we call osmosis. There are also special channels we'll talk about later this semester called aquaporins, which allow water to really flow in or out. These things can't get through. Anything too big to squeeze between the phospholipids won't get through. And then other than water and alcohol, polar molecules, things like glucose and albumin, can't get through the plasma membrane. Ions, because of their electrical charge, have a bit of a magnetic field or a force field around them. They cannot get through the plasma membrane. And then proteins, which tend to be large and polar, sort of have everything working against them. And so we'll see proteins trapped within the cell and they can't get out. They're supposed to be there. We'll see other extracellular proteins trapped on the outside of the cell and they can't get in, and that's how it's supposed to be because the plasma membrane is semi-permeable. Now, you might be asking right now, why should I care? Make me care, Jay. Well, here we go. pharmacology, right? Drugs, mechanism of action, the reason that our patients can get sick or die from electrolyte imbalances, and why they might have seizures. Why does my favorite cheeseburger slowly kill me? And how does puberty transform a girl into a woman? Really, at the heart of all of these phenomena is the fact that the plasma membrane will let these things easily through and not so much with those other things. So you might pause the video right here and think about it. Which things can and can't get through? Okay, other than passing directly through the plasma membrane like a ghost through a wall, there are other ways that we can get things in or out. Opening doors or pushing them through vesicles or pumps. And so that's what this next bit's about, passive and active transport. There are two types of diffusion: simple diffusion, where things just flow from one concentration to the other, and facilitated diffusion, where they're flowing with that concentration gradient, but they're being helped through, like we had seen in the previous video with that little carrier protein. Simple diffusion goes just right through an open channel, but that facilitated diffusion requires a carrier protein. Osmosis is the movement of water toward a high solute concentration. The little phrase is water follows salt. And then filtration, you know what this is. Coffee filter, oil filter, furnace filter, screen in your window, lets the breeze through, keeps the bugs out. At the tissue level, and rarely at the cellular level, we can see filtration works the same way. Tiny holes let some things through, but other things can't get through. The transport mechanisms on this side are fundamentally different because they require an energetic boost by ATP. Active transport. These, by and large, are ways of moving things where the things don't want to go that way. Here's what I mean. Diffusion just happens, right? It's the nature of the universe for a concentrated gas to slowly spread out, to diffuse. We don't have to make it spread out. I don't have to give it energy. It just happens. But in this case, active transport pumps might be a way of collecting a gas into a dense little clump. The gas doesn't want to go into that dense and crowded space. We can make it go there. Endo and exocytosis are vesicular transport mechanisms. This means we're going to use a vesicle to pump something out in exocytosis, or pull the cell membrane in to form a vesicle and package our stuff in endocytosis. Key concept of diffusion is that things flow from high concentration to low concentration. Right? If I drop a little sugar cube in a beaker of water, I don't have to stir it up or heat it. Eventually, it will spread out. The reason it spreads out is that everything in the universe is sort of jiggling, right? The warmer the environment, the more jiggling there is. It's a fun word, isn't it? Jiggling. Your body at 98.6 degrees is plenty warm to be vibrating all of the molecules in your body. The water is jiggling and bumping into other things, and oxygen is jiggling around and bumping into the glucose, which is jiggling and bumping into the cell membrane. So that's why everything moves around. That's why diffusion happens. Ambient energy, like your body heat, causes things to vibrate and to move around. Like if kids throw a bunch of pool balls out on the table, they just roll and bump into each other randomly. In the event that these lipids are sent careening in this direction, they will go right through because the plasma membrane is permeable to lipids. These ions, however, if they went careening in this direction, they would bounce off of the plasma membrane because the cell membrane is impermeable to ions. So look at this. Even within simple diffusion, we actually have a couple different kinds. Diffusion through the plasma membrane, in this case of lipids, or diffusion through a channel. In either case, this is simple diffusion. Osmosis works in a different way. Look at this. I have a semi-permeable membrane, and I have some big polar stuff in here. This could be salt, or it could be urea, it could be glucose, doesn't really matter. Because these things are big and polar, they will not diffuse across the plasma membrane. So we don't have to worry about this column of water getting contaminated. It's going to stay on the inside because these things can't get out. However, because the membrane is permeable to water, and because this water is jiggling around, it will occasionally pass through in this direction. Here's the key concept. The water sticks to the salt. There is a sphere of hydration, a tiny circle of water around each of these polar molecules. So, although everything in this side is jiggling, the water is stuck to this solute and it can't jiggle back out. Over time, more water jiggles in than gets out, and what we see is that that column of water actually moves up. It'll move up to the point where atmospheric pressure or hydrostatic pressure balances it out, and then we get to equilibrium. But the movement of water towards that salty concentration is called osmosis. Now, we love to do all kinds of things with this word in physiology. We modify it so that we can talk about the concentration of two solutions as being isoosmotic, or hyperosmotic, or hypoosmotic. This is maybe interesting language, but really the purpose of this is to help us understand why, for example, a patient should never be given a drip of pure water, right? Oh, patient's dehydrated, let's hang a bag of water. Well, even if you could find it, pure distilled water, you would never want to do it because it would cause such an osmotic shock to the patient that you might kill them. You want to make sure that your solutions, by and large, have the same concentration, isotonic or isoosmotic solution. Here we go, more of the same. You could pause the video right here to see why the cell increases or decreases in its volume. Embedded within your downloadable PowerPoint, you can watch this video and this one. Really helpful, help you understand how facilitated diffusion works. Okay, endocytosis is the process of forming a little dent in the plasma membrane. That's done, by the way, by the puppet master pulling in on these cytoskeleton. Is none of it shown here, you have to just imagine. But right here, there would be little fibers being pulled in. This is called an invagination. And then ultimately, the edges of that invagination touch, and suddenly we have a phagocytotic vesicle brought in. It's actually a bit more clear maybe back here on this picture, right? You can see that the plasma membrane of the phospholipid bilayer of the plasma membrane merges with itself to become a tiny bubble of phospholipids. That's endocytosis. And you can watch videos in our Chapter 3 Blackboard lecture folder that show you this. Exocytosis is exactly the opposite, and that's what we see with the Golgi typically, right? Bubbling off a secretory vesicle, which then fuses with the plasma membrane, and the proteins are secreted out of the cell. All right, now let's see if I can find my way back. Phagocytosis is a form of endocytosis by which a solid particle is brought into the cell. It comes from the word phage, which means to eat or swallow. Pinocytosis is also endocytosis. We form a vesicle, but you have to imagine that this would just be liquid and not this little bean. So I remember this, of course, by thinking about Pinot Noir, a delicious red wine. Or Pinot Grigio, if you know that one, right? Pinot. We drink Pinot. The cell pinocytoses liquid. Not really shown here, but you can see in your book there is also receptor-mediated endocytosis, where we can bring in lots of little particles which hook up to receptors, and when there is a critical mass of those, then the vesicle is brought in. Here's the third form of active transport, the active transport pump. Kind of funny that the active transport pump uses ATP. Look at that, its initials. Whoa. Okay, maybe you're not impressed by that. How about this? ATP is used to push substances from low to high concentration. Think about that for a second, people. This is remarkable. We rarely see this in the natural world. The natural tendency of things is to diffuse from high concentration to low concentration, but it is nearly only living things and ATP which can concentrate things, right? You can eat a tiny low concentration of calcium and slowly over time accumulate it in your bones through active transport. And this one here, the poster child for the active transport pump, the so-called sodium-potassium pump. 20% of your calories every day go to feed these beasts. There are trillions of them throughout your body, by the way. The ATP, active transport pump, known as the sodium-potassium pump, is what generates your voltage, people. The electricity that flows along your nerves and muscles, that electricity is made possible by this, generating a very high concentration of sodium on the outside of the cell and a very high concentration of potassium on the inside of the cell. That doesn't want to happen naturally, right? Things want to flow until they reach equilibrium. And these ions are continually leaking through little holes and crannies, and the sodium-potassium pump has to continually push these out and push these in. Just like trying to push people into an already crowded elevator, these sodium ions do not want to go out of the cell. We have to use energy to make them go out. These potassiums say, hey, it's so crowded inside, we don't want to go in there. But the sodium-potassium pump grabs them and pumps them in, and thereby generates voltage. So you can think and understand what I'm talking about right now. Beautiful video. You should watch this one. Okay, I'll be back in a few minutes with our next video. Need to go get something to drink? You hungry? Go ahead. I'll wait.